EDX Core Pure Sequences in Series 2 Induction. Using induction to prove results about matrices. Induction can be used to prove various results about matrices. Often this involves proving a result about a power of a matrix. For example, we can use induction to prove that the matrix 3 minus 4, 1 minus 1 to the power n can simply be written as 2n plus 1 minus 4n n minus 2n plus 1. Just a reminder about the process for proof by induction. The first step is to check it is true for the first term, in other words n equals 1. Then the assumption, step 2, that if the result is true for any individual term, usually k, then it will also be true for the next term, k plus 1. And then the final conclusion step, that if the result is true for n equals 1, and if it's true for n equals k, it is also true for n equals k plus 1, then it must be true for all integers of n at least as big as 1 by mathematical induction. So we're going to prove this result by induction. So step 1 is we need to consider n equals 1. So first we look at the left hand side of the problem. We get 3 minus 4, 1 minus 1 to the power 1, which is obviously 3 minus 4, 1 minus 1. If we look at the right hand side, where we need to be a little bit more care here, n equals 1, remember, so this is 2 times 1 plus 1 minus 4 times 1, which is minus 4, 1 and minus 2 times 1 plus 1. And if we tidy this up, we get 3 minus 4, 1 minus 1. So it is indeed true for n equals 1. Now we've got to make the assumption that it will also be true for n equals k. So we're going to assume that that statement is true. If that statement is true, then we need to show that the corresponding statement for k plus 1 will always also be true. So this statement here is our assumption, and we're assuming that's true, and we can use that statement when we think it's appropriate to use it in the algebra. And this statement at the end is our target. That's the one we're trying to produce. So we now consider the matrix to the power k plus 1. We know that that can be written as the matrix to the power k times another matrix, just using laws of indices. Now we can use our assumption step. We have assumed that the matrix to the power k can be written as 2k plus 1 minus 4k, k minus 2k plus 1. That's our assumption being used. We have to multiply that by 3 minus 4, 1 minus 1. So very carefully multiplying these matrices together. So multiplying the top row by the first column first, we're going to get 6k plus 3 minus 4k. Now I'm going to multiply the top row by the second column very carefully. That's minus 4 lots of 2k plus 1 minus 4k times minus 1. Now I'm doing the bottom row by the first column. So that's 3k minus 2k plus 1. And then the bottom row by the second column is minus 4k, and then minus 1 times minus 2k plus 1. Now we're going to simplify each element. So the top left element is 2k plus 3. Top right element is minus 4k minus 4. Bottom left element is k plus 1. And bottom right, when we expand the brackets carefully, is minus 2k minus 1. That's not quite in the form we need it to be. We need it to be in the form that we were aiming for. So we need to show that this can be written in a slightly different way. So 2k plus 3 is the same as 2 lots of k plus 1 plus 1, which is the form we were aiming for. The next element can be written as minus 4 times k plus 1, which is the way we need that element to look. The bottom element is correct at k plus 1, and the bottom right I'm going to write as minus 2 k plus 1 plus 1. So that is the form we needed for the matrix to the power k plus 1. As you can see there, if you can follow the working through. So hence, if it was true for n equals k, and that was the first thing we assumed in our first step of working, it will also be true for n equals k plus 1. So, if the result is true for n equals k, then it is also true for n equals k plus 1. As the result was true for n equals 1, it must be true for all integer values of n at least as big as 1 by mathematical induction. In the next session, we'll be using mathematical induction to prove results about divisibility.